Hi guys, this video today is going to cover rotational dynamics. We're going to talk about moment of inertia, torque, acceleration, which we've already talked about before, but we're just going to do a couple of examples to help us understand that a little bit better. We're also going to talk about rolling versus sliding, and in addition to that, we're going to talk about energy and how rotational energy works. So first of all, some equations that you need to remember. Take a second to write those down. Let's just go ahead and jump into the first example. So we have a diagram here, the moment of inertia. When you have a system of points, and that's basically what these are, is point masses, then we just do the plain old mr squared. Remember, inertia has several different formulas. It could be 1/2 mr squared, it could be 2/5 mr squared. In this case, we just use mr squared. So because we have two different point masses, then we have m1 r1 and m2 r2. And of course, we square the radius. So if we take a second to do that, so our first point is the 2 kilogram. Its radius, basically meaning the distance away from the pivot point, is 2 meters. We square that. Our other one is 4 kilograms, and its distance is 1 meter, and we square that. And so we get 8 kilogram meters squared plus 4 kilogram meters squared, and we add those together, and that adds up to 12 kilogram meters squared. That means that this system is going to have a moment of inertia of 12 kilogram meters squared. Remember what inertia is. It is something's ability to sit or ability to move, and so that's what that is. The torque of the system, well, the sum of the torques is going to be the force times distance of each one, and they're going to be added up together. Okay, when we're looking at net torque, we have to think about direction. And so this mass, if it was just pivoting around this by itself, it would go this way in the negative direction. That's clockwise, which is negative. This one would go in the positive direction because it's counterclockwise, which is positive. So when we do that, we have to consider the negative and positives in that. So I'm going to start plugging in numbers for my force and distance, but I have to call this one negative and this one positive. And so I have a negative 2 kilograms gravity and distance plus 4 kilograms gravity and distance. And if I multiply these, I get a negative 4g here, and I get a positive 4g here. And so that just adds up to 0. My torque is 0. And torque is measured in Newton meters. What that means is it's balanced. Okay, if its net torque is 0, it's balanced. It is not going to spin either way. Now, in a real situation, probably, something's going to make it spin, whether it be, someone breathing on it or whatever. But equation-wise, it is balanced and it's not going to spin until you do something to it. You push it, you breathe on it, whatever. Which means the next question, if it is released from rest, what is the initial angular acceleration of the system? Well, that's going to be 0. Okay, it's because we just talked about it, but also if you put it into the equation, our torque is 0, and then our moment of inertia is 12, and then our alpha is what we're looking for. Well, that alpha has to be 0 in order to make that 0. And so just to reiterate, that is in equilibrium. It's not going anywhere at this point unless something hits it. Okay, question number 2. What is the moment of inertia for a 10.8 kilogram sphere of a radius 0.648 meters when the axis of rotation is through the center? Now, again, remember I mentioned this before, but these equations, you do not need to memorize all the different inertia equations. They would be given to you on the AP test where you need them. So it'll have it in the sentence of the question at the times that you need it. Okay, so I'm just going to take this equation, they've given it to me, and I'm just going to plug in my numbers. So my inertia is 2/5 times the mass, which is 10.8 kilograms, times the radius, which is 0.648, and we're going to square that. We're going to do that on our calculator, and we're going to get a moment of inertia of 1.8 kilogram meters squared. That's just basically how you look at inertia. Like, that's how you calculate inertia. When we talk about moment of inertia, it's a number. I mean, in physics, it has to be a number that we quantify it with. So this is basically a quantity that tells us how easily that will roll, how easily that sphere will roll, or conversely, how difficult it is to get that ball rolling. Okay, so that is for a sphere. That 2/5 is the equation for a sphere. If we just have a ball being swung on a rope, in this case, it's a little bit different because what we are looking at is kind of a point mass, similar to what we were looking at the beginning, that we have this point going around in a circle, but we really consider this like a point. And so that's what's going on in the next question. Number 3, if we have a ball being swung in a circle, well, now the ball is just, a point along that circle. And so now we use this equation. And again, you don't have to memorize these equations. They will typically be given to you. Now, it's not being given to you at this point, and it also was not being given to you at number 1 because they are seeing if you understand that this is just a point. Okay, so you do have to memorize that when it's just a point going in a circle, you're going to use this formula. Okay, so if we use this formula, we're just now going to plug in some numbers. Our mass is 2 kilograms, and our radius is 0.5 meters, and then we have to square that. And so our moment of inertia, the numerical quantity that it comes out to be, we're going to multiply that together and get 0.5 kilogram meters squared. So once again, the idea here is this is a quantity that quantifies how easy something is to swing or roll, or how difficult it is to swing or roll. And so basically, to think of why would we ever need this kind of thing? Well, sometimes you want whatever it is you're spinning to be able to spin really easily and really freely. Other times you want it to be a little bit more solid and not spin so easily. And so this is what we look at is, what is this quantity? How easy is it or how difficult is it to get moving? All right, next question. 5 newtons of tangential force is applied to the rim of a 5 kilogram thin hoop with a radius of 0.75 meters. What is the resulting angular acceleration? I'm going to draw a diagram, and I'm also going to list my information just to kind of help make sense of what's going on. So we have a force of 5 newtons, we have a mass of 5 kilograms, we have a radius of 0.75 meters, and the acceleration is what we are looking for, the angular acceleration. As far as a diagram goes, what we have is we have a thin hoop, should be round, mine's not exactly round. This hoop itself has a mass of 5 kilograms, radius of 0.7 meters, and we have a 5 Newton tangential force applied to it. In other words, we are applying this force of 5 newtons, and we are applying it here tangentially to the circle. So not at some kind of, skewed angle, but applying that to the edge of the tangent. All right, we are looking for angular acceleration, but it's going to take us a little bit to get there. We're going to have to go through some different steps to get there because we know that torque is force times distance. So we have to figure that. We have a 5 Newton force and we have a 0.75 meter radius. And so if we multiply that out, we get 3.75 Newton meters. That's our torque. We also know that inertia, moment of inertia, is mr squared. So that is 5 kilograms times 0.75 meters, and we square that. We put that into our calculator. Finally, we know that torque is moment of inertia times acceleration. And we just calculated our torque to be 3.75 Newton meters. We just calculated our moment of inertia to be 2.8125 kilogram meters squared. So now we can go ahead and calculate the acceleration. You could move your equation around before your calculations or after, it doesn't matter. So I went ahead and moved my equation around ahead of time. It doesn't matter, you could do it the other way, but you end up dividing 3.75 Newton meters divided by 2.8125 kilogram meters squared. in class, I'm going to show you how these units can cancel, because newtons is kilogram meter squared, and so that's going to cancel with some of these. And anyway, it leaves us with 1.33 radian per second squared. That is our angular acceleration. And so just to kind of double back around, remember that we had force equals mass times acceleration, and we know that torque equals inertia times acceleration is the rotational version of that. And if we had force, then we had acceleration. Well, same thing here. If we have torque, then we have acceleration. If we are applying if we are applying a force, then it's going to be accelerating. And that's where we're getting this angular acceleration from. Okay, let's talk a little bit about rolling versus sliding. When we talk about inclines, if the object on the incline is round, it doesn't move linearly. It doesn't slip down the ramp, it rolls. Well, what's going to cause it to roll? Like, why isn't it slipping? Well, the object has both linear and rotational motion down the ramp. So as this is object, whatever this object is going down the ramp, it is moving both in the rotational way and linear way. And static friction is what's causing it to rotate. If it didn't have any static friction, then it would be like ice. And in that case, it would slide down the hill. And so this is a little bit like, if you have this ramp and you have something like a block sliding down the hill, well, that's just going to go straight down. Whereas if you had a hoop or a ball or anything that's round, it's going to roll down the hill, and they are going to be different. But friction is what's causing that. If there is no friction, like an icy hill, then it will not roll, it will just slide. And just a little side note here, it is possible for an object to both roll and slide, and this is called slipping, and it involves kinetic friction. We are not going to do calculation for this, as it causes the object to over-rotate or under-rotate, and the linear and rotational accelerations are not related. So it's going to be a much different situation. We're in Physics 1, so we're just going to deal with plain old rolling or sliding. Let's turn the page.